Welcome to the second video covering the material in Chapter 3. In this video, we're going to cover measures of variability. In other words, measures of how spread out our data is. Your textbook covers two concepts that we are not going to cover in class. Your textbook covers the range, which is simply the maximum value in the data set, minus the minimum value in the data set. Your textbook also discusses the interquartile range. The interquartile range is the difference between the 75th percentile and the 25th percentile. It's a lot like the range, except that it is not as influenced by extreme values. We're going to focus on talking about the variance and the standard deviation in this video. Your textbook also covers the coefficient of variation, and you should read about the coefficient of variation on your own. Variance. The variance is the most standard measure of variability, and it utilizes all of the data in the data set. What it really measures is the average squared deviation from the mean. Here are formulas for the variance. There are two formulas because, once again, just as when we talked about measures of central location, we are going to concern ourselves with a sample of data and the associated population parameter. We will often collect the sample, calculate the variance for the sample, and use that as what I called a point estimate of the corresponding population parameter. So let's note the differences between these two formulas and try to interpret what these formulas actually mean. In the formula on the left for the sample, we denote the sample variance as S squared. And what you will notice is that I am calculating for each observation the difference between that observation and the mean, which we calculated in the previous video. I'm going to take the difference between each observation and its mean, and I'm going to square it. I'm going to do that for every single observation that's in the data set, and then only after taking those differences and squaring them am I going to add them all up. Once I have added them all up, as signified by the summation sign, I'm going to take it, in a sense, an average of those squared deviations from the mean by dividing by the sample size minus 1. So why do we divide by n minus 1 in this left-hand equation? Well, the answer to that question is that from the sample, we had to calculate x bar. Now, we square each one of these differences between the x value, the observation, if you will, and x bar, because if we were to add up all the deviations from the mean, we would obviously get an answer of 0, since the mean is in the middle of the data set. We therefore lose 1 degree of freedom in calculating the mean. What that means is that really we only have n minus 1 independent pieces of information. Once we have calculated xi minus x bar for n minus 1 of the observations, the last deviation from the mean must satisfy the requirement that the sum of the deviations from the mean is equal to 0. Therefore, we correct our denominator for degrees of freedom that we lose in calculating x bar. We divide by n minus 1. But in essence, what this is it's an average squared deviation from the mean in the data set. So it has a very clear interpretation as a measure of variability. When we look at the population, the formula looks very similar. The exception is that we denote the population parameter with the Greek sigma squared. Also note that we've replaced x bar with mu, where mu is our population parameter for the population mean. We also divide in the denominator here by n, which is the size of the population, rather than n minus 1, as we did in the case of the sample. So these formulas are very similar, the one on the left being a point estimate of the population parameter on the right. The standard deviation of the data is basically just the positive square root of the variance. The great thing about the standard deviation is that it's measured in the same units as the data. It makes the standard deviation much more easy to interpret than the variance. It's pretty simple then to go from the formulas for the variance to the formulas for the standard deviation for both the sample and for the population. We simply take the square root. If we're going to take the square root of x squared in order to get the sample standard deviation, then a natural choice for a symbol to stand in for the standard deviation is s, and likewise for the population parameter, sigma. Let's go through an example. The variance and standard deviation of our rent data set. Here I have reminded you of the calculation of the mean in this data set, which was accomplished on the previous slide, 590.8. How are we going to calculate the variance and then from the variance the standard deviation? Well, what we're going to do is we're going to take each value that is in this table. We are going to subtract the mean of 590.8 from each value. We're going to take that difference and square it. And only then are we going to take all of those values and add them up. And then we are going to divide by the sample size, minus 1. We will divide by 69. So for the first observation, we have 525 minus the 590.8. We take the difference between those two values, and only after taking the difference between those two values do we square the answer. And the answer is 4,329.64. We are going to do this for every single observation that is in the table, and we're going to add up all of the results. When we do so, we're going to get a very large number, 206,735.2. With 70 minus 1 degrees of freedom, we are going to take the 206,735.2 and divide it by the 69. The answer then is that the variance is $2,996, well, let me put it this way, 2,996.16, but that's not really in dollars, right? This is the variance. It's not measured in the same units that my variable rent is measured in. It's really measured in dollars squared. In order to get a measure of variation that's in dollars, the same units that rent is measured in, we take the square root. The square root of $2,996.16 is $54.74. That is measured in dollars. And that is the standard deviation in this data set. Relative location and detecting outliers. In order to talk about relative location in a data set and apply Chebyshev's theorem, I first need to discuss z-scores with you. We will discuss z-scores and then apply them to Chebyshev's theorem. Then I will tell you about the empirical rule, and finally, briefly, I will tell you how to use z-scores to detect outliers. A z-score is basically a standardized value. What it denotes is the number of standard deviations that a piece of data in the dataset is from the mean. It's pretty obvious from looking at the formula for a z-score. If you have a dataset with 70 observations, such as our rent dataset, then there are going to be 70 different z-scores. So I index is the observation in the data set. For each one of the observations in the data set, xi, we calculate how far it is from the mean simply by subtracting the mean from it. Note then that the difference between xi and x bar can either be positive or negative. If xi is greater than the mean, then the value of the z-score will be positive. If xi is less than the mean, then the value of the z-score will be negative. We take this difference between xi and x bar, and in a sense we standardize it by dividing it by the standard deviation. That tells us how many standard deviations away from the mean the observation xi is. Here's an example. For apartment rents, I'm going to calculate the z-score of the smallest value in the data set. The smallest value in the data set in our previous table was equal to $525. That was the cheapest rent in the data set. We also know that the mean in the data set was 590.8. So if we take the difference between 525 and 590.8, we have the amount in dollars that the smallest value is below the mean, and then if we divide that answer by the standard deviation, which we calculated on the previous slide, of 54.74, we get an answer of minus 1.2. What that means is that the smallest observation in the data set is 1.2 standard deviations to the left of the mean. And I know it's to the left of the mean because of the negative sign in the z-score. Chebyshev's theorem is often very useful for determining the least percentage of data that has to lie within a certain number of standard deviations of the mean. So we use z-scores in Chebyshev's theorem. And Chebyshev's theorem states that at least 1 minus 1 over z squared percent of the items in any data set, or the observations in any data set, will be within z standard deviations of the mean, where z is any value greater than 1. So we can only use z-scores in the formula that are greater than 1. And note that basically what this tells us is the minimum percentage that need to be within z standard deviations of the mean. The actual number of observations within z standards of the mean could be larger than the value that we calculate with Chebyshev's theorem. Z also need not be an integer. Chebyshev's theorem. Here is an example. At least 75% of the data values must be within 2 standard deviations of the mean. At least 89% of data values must be within 3 standard deviations of the mean, and at least 94% of data values must be within 4 standard deviations of the mean. The thing about Chebyshev's theorem is that it applies to distributions of any shape. The distribution of the data can be skewed to the left, skewed to the right, or it can be bell-shaped, and Chebyshev's theorem holds. The following rule that we're going to cover next, called the empirical rule, will only apply to distributions that are symmetric and bell-shaped. First, here's an example of Chebyshev's theorem. We're going to apply this to apartment rents. Let's let z be equal to 1.5. That qualifies for Chebyshev's theorem because we need a z that's greater than 1, and there's no restriction that z be equal to an integer. In our apartment rent data, x bar is 590.8, and we know that the standard deviation is $54.74. Using Chebyshev's theorem, we plug the value of z into the formula. That is 1 minus 1 over 1.5 squared. Carrying out that very simple calculation, either in Excel or on a calculator, will show you that 56% of the observations, or more, must lie within 1.5 standard deviations of the mean within that data set. Okay, so x bar minus z then would be the 590.8 minus 1.5 times the standard deviation, which is 54.74, means that we have a lower bound for this range of $509, and the upper bound is x bar plus z times the standard deviation. The only difference between the formula that I'm underlining now and the one that I underlined previously is that I changed the minus sign from a plus sign to get the upper bound of the range between which the values of the data must lie. And so changing from a minus to a plus, we get a 673. So 56% of the observations or more must lie in between values of 509 and 673. In all actuality, if you go back to the data set and count the number of values that are in between 509 and 673, and you divide that number by 70, you'll find that 86% of the rent values actually fall between those two values. And that, of course, is consistent with Chebyshev's theorem, because Chebyshev's theorem tells us that 56% or more of the values must lie between 509 and 673. That is the way Chebyshev's theorem is used. The empirical rule is consistent with Chebyshev's theorem, but we can be a bit more precise if we're dealing with distributions that are symmetric and bell-shaped. Here is the empirical rule. 68.26% of all the values for a normal random variable or a bell-shaped distribution will be within plus or minus 1 standard deviation. 95.44% will be within 2 standard deviations, and finally virtually all of the observations will be within plus or minus 3 standard deviations of the mean. Here it is graphically. You can see the mean at mu here for the population. If I move 1 standard deviation to the left, I'm at mu minus 1 times the standard deviation, where the standard deviation here for the population is denoted by delta. Moving to the right of the mean, where it would have z values that are positive, I'm going to take mu and I'm going to move 1 standard deviation to the right by adding rather than subtracting. In between those two values, we will have 68.26% of the observations. If I move 2 standard deviations away from the mean, then I must move to the left to mu minus 2 times delta and to the right to mu plus 2 times delta. There will be 95.4% of the observations in the data set that fall in between those two values. And finally, if I move 3 standard deviations to the right and 3 standard deviations to the left, and I look at the frequency of the data, 99.72% of the values will lie in between plus or minus 3 standard deviations of the mean. The empirical rule is very useful for thinking about the normal and standard normal distribution, which we will cover in more detail 2 or 3 chapters from now when we talk about continuous probability distributions. We can use these concepts to detect outliers in our data set. An outlier is an unusually small or unusually large value in the data set. And particularly in small data sets, having outliers in the data set can bias our results and give us unreliable estimates. A data value with a z-score less than minus 3 or greater than plus 3 can be considered an outlier. An outlier might be an incorrectly recorded piece of data. When people are typing in data manually, for example, it's very easy to miscode a particular data value. It could be a data value that just didn't belong in the data set at all, or it could be a correctly recorded data value that does in fact belong in the data set, which makes it sometimes more difficult to decide what to do with the outlier. Often it's best to present two sets of results, one that include the outlier and one that does not include the outlier. In many cases, particularly in a large data set, your conclusions might not change all that much. So what we would do with the typical data set is we would calculate the z-scores for all the values in the data set and check to make sure that none of them are smaller than -3 and none of them are greater than +3. Here is that technique applied to our apartment rent data set. What we have here is a table of z-scores. You can see that the smallest z-score is -1.2. So on the lower end of the data set, there's no indication of any outliers. The same appears to be true for the upper end of the data set, where we have 2.27. 2.27 is less than 3. So it would appear that at the upper end of the data set, we do not have any outliers either.